Let's go over activity number 3 together in case you had a chance to practice yourself. So first of all, continuity checklist. If we want to apply to the function named g of t and I want to know whether my function is continuous at the point of 3 or not, then we need to go through 3 steps like we discussed in class. The last step must be comparing the function value with the limit. The first 2 steps, it doesn't matter which one you go first. So you're going to say g of 3, the function value exists, right? And also you're going to say the limit as t approaches 3g of t. The limit of function g when t approaches 3 exists. And the last thing is the function value and the limit. They actually are identical to each other. So like I said, step 1 and step 2 are interchangeable, but you can only keep the last step in the end. So we can try to use different kind of online graphing calculator to help us to plot the graphs of those functions. But this basic idea is to go over the continuity checklist over and over again to give you a better visualization and understanding of the idea of continuity. So the first problem is I'm asking you to plot the graph on the, Desmos calculator. So it's quite easy for you to realize when it's -3, your input is -1. When it's 0, it is 2. So what you are going to end up with is a graph that looks like that. When you are approaching to -3, you will be approaching to the point -1, and your function value is -1. Those two, your function value and limit, they do match. So your function is a continuous function. In general, for a linear function, it's always continuous. So solve a limit problem for linear functions is simply just solve for the function value. You can always plot the graph of different lines, and this would be your final observation. The next problem I have is limit of 3x squared minus 1 over 2x plus 1. So I have the graph plotted here. What I want to happen is to plot the graph near the point of 0. As you can tell, my function goes through the point 0, 1, -1, and I'm approaching to it from both left and right. So this is what I end up with. If you don't trust me, you can do the quick checking of function value substitution, and then you end up with -1. So yes, they do match with each other, and my function is continuous because they are exactly the same thing. So this is a rational function, and this rational function is continuous. Its denominator is not 0, so for rational functions, it's still continuous as long as my function value exists. So in other words, the denominator is not 0. Let's look at something slightly more interesting. If I'm approaching to 2, I have the graph of the function here. This is my 2. If I'm approaching to 2, clearly my function goes towards upwards and downwards. So clearly I don't really have a limit. And if you look at the function value by plugging into 2, you have 2 squared minus 4. You end up with 0, denominator being 0. Your function value does not exist. So you don't have a limit, you don't have a limit. You don't have a limit, you don't have a function value. Actually, by having one of those to be does not exist, your function is not going to be continuous. So a function that's is not continuous as long as the denominator is 0. Okay, I don't even care about the numerator. It's just as long as the denominator is 0, my function is not continuous because the function value, let's write it down, because the function value does not exist. So let's move on to the next step. This problem, as we discussed in class, is mathematically equivalent to this statement as long as x plus 3 is not 0. In other words, as long as x is not -3. So what I boxed here is equivalent to that problem. And if you were trying to find the limit, the simplification says as long as you are not going to be at exactly -3, they are the same thing. So mathematically, those two are equivalent problems. I also plot the graph on the right. So you can tell as you are approaching to the point of -3, you are getting towards the height of -1. My function value does not exist. No surprise, its denominator is 0. So those two answers do not match. My function is not continuous. So this is, again, a rational function. A rational function is not continuous when the denominator is 0. So This next thing says if a function is not continuous at the given point, does that mean the function do not have a limit? Well, no, it's not really the case. In this particular example, you can see the function have a limit at that point, but it doesn't really have a function value. This is what we call a removable discontinuity. So the graph actually looks like a continuous curve with a hole in the middle. So if we move on with the next problem, the piecewise function, I have plotted the graph on the right. So if I'm approaching to 0 from both the left and right, you will be getting the limit to be both 0. Hence, my function has a limit of 0. Function value is easy to find out. So you can tell, since they are exactly the same thing, we can get to our conclusion quite easily. The next piecewise function is slightly more interesting. The graph goes like what I have here. When I'm greater than or equal to 0, it's solid dots. Up here, it is a circle. When you try to identify the limits, the left one and the right one, you are approaching to different height. One is 2, one is -2. So I can fill in, I end up with right limit being -2, left limit. Sorry about the typo here. Left limit is +2. Well, since they do not match with each other, the limit doesn't really exist. Function value is the one with a solid dot. It's down here. So what I have is -2. Clearly, limit doesn't exist, indicates your function is not continuous. So comparing to the answer to problem 6 and problem 7, both are piecewise functions. Both were asked what's going on at the point where it was cut into 2 pieces. One is continuous, other one is not continuous. So my conclusion is for piecewise functions at the cutoff points, I have to do a discussion about the continuity property. There's no clear answer whether it's continuous or not. So the rest are true and false questions. For a limit problem, if the denominator is 0 after substitution, the limit does not exist, which is false. I would recommend you to look at problem, this one here. So look at problem 4 above. And for a limit problem, if the denominator is 0 after substitution, the limit may still exist, which is true, which is exactly problem number 4 as shown at the top of this page. For limit problem, if the denominator is 0 after substitution and the limit exists, the value of the function must be 0. Well, not really. Again, look at problem number 4 above. I don't really have a function value. For limit problem, if the denominator is 0 after substitution and the limit exists, the value of the limit must be 1. Exactly the same thing. I have, as long as the denominator equals 0, my function doesn't have a value. Okay, that never have this value. For a rational function, if the denominator is 0 at the point of 2 and the function is not continuous, then the function must not be continuous as 2. It is definitely true, because if that's the case, then the function value, the f of 2, does not exist, which violates the first rule in our discussion for continuous property, and therefore we get to the conclusion that it's not continuous right away.